Almost 20% of all crimes in Australia involve a gun. Forensic scientists and police analyse evidence to track down criminals. When a crime involves a firearm, bullets are an important piece of evidence. Clear. What they're doing here is shooting a suspect's gun to try and match the bullets to those recovered from a crime scene. When a gun is fired, tiny scratches are left behind on the bullet. These scratches are called rifling marks. Shooting into the water prevents these marks from being damaged on impact. Forensic scientists use microscopes like this one to examine these scratches in detail. All bullets fired by the same gun will have the same marks. If a bullet from a crime scene matches a gun, a suspect can be linked to a crime. But it means police and forensic scientists need to have both the gun and the bullet to examine. But sometimes this isn't possible. So what happens if the gun can't be found? Or if the bullet fragments after it's fired? Forensic scientist Anna Bradley is on the case. She's researching how just bullets and even bullet fragments can be used to catch criminals. Before we meet Anna, I'm going to make some bullets for her to test. Bullets are made mainly of lead, and the lead usually comes from scrap metal. There are traces of other metallic elements in bullets too. Some of these are impurities, but others are added intentionally. I'm going to melt down this lead together with the other metal elements in the scrap and make my own batch of bullets. Because the bullets I've made are from the same batch of scrap, they should contain the same amount of the same elements. If we give these bullets to Anna to test, she should be able to tell that they were from the same batch. Hey Anna.
Hi Toby.
What are you doing out here?
I'm just dismantling these bullets to see if their composition matches those taken from a crime scene.
Well, I've got a test for you. Do you think you could tell me if these bullets came from the same batch?
I sure can, but if you let me finish up here first, then I'll be able to take your bullets back to the lab and test them. Should we go?
Yeah.
Well, I need a small amount of material from the bullet, so I'm going to use this drill and drill out a very tiny amount that I can analyse later. I'm then going to take this small amount of material and place it on a plastic disc. Because the differences between different batches of bullets is so small, we need to use accurate equipment to determine this, and that's in the other lab. I use a laser to blast free some particles. The particles are analysed by this machine. It's called a laser ablation, ICP-MS. We can watch what's happening on the screen here. This screen shows all of the data being collected. I've compiled all the information from our analysis. What we've got are different elements on the bottom here and their relative amounts on the side. And this fingerprint or pattern is unique to your test bullet.
What happens to the particles inside the ICP-MS?
Well, the ICP-MS is an inductively coupled plasma mass spectrometer. And what that does is sort the different particles. And how it sorts them is by their mass. Let's pretend that these are the particles. You and I will sort them by colour, but the ICP-MS will do it by their mass.
Oh, and it's starting to make a pattern like our graph.
It is.
So what happens to the particles once they're separated?
Well, the spectrometer counts the particles. There may be millions and even billions of a particular particle, and that way we get an understanding of how much there is of each element in the sample.
And how did my test bullet go?
Well, this is the elemental pattern for the first bullet that you gave me. And this is the pattern for the second. And what you can see is that they have the same amount of each of the different elements in, and they've come from the same batch.
What would our graphs look like if the bullets weren't made from the same batch of scrap?
Remember that bullet that I was dismantling earlier? I also analysed it, and this is its elemental pattern. And you can see that your bullet has a lot more arsenic than mine.
Where's lead on the graph?
I don't measure the lead, and that's because there's so much lead in one bullet that it actually makes it really hard to work out these tiny differences between the other elements.
Has this method been used in criminal investigations in the past?
It has. The FBI used to use a similar technique where they measured 7 elements, but I measure 19 now, which makes my analysis and interpretation a lot more reliable.
How are you hoping to use your new technique?
Well, the police at the moment don't have a technique for analysing bullets, so I'm hoping that my research will give them a new opportunity in forensic science.
Wow. Thanks, Anna. It's been really interesting.
Thank you.
It's the tiny differences in the mass of elements that's useful evidence. Now, criminals not only have to worry about their own fingerprints, but the fingerprints their bullets leave behind.